Wait a moment.
Okay.
Can you hear my PowerPoint?
Yes, that's fine. Please start, please.
Okay.
Hello everyone, my name is Rongrong He, a PhD student from Shanghai Advanced Research Institute. My supervisor is Professor Tao He. My topic is unprecedented magnesium lithium separation using layer-by-layer based nanofiltration hollow fiber membranes. My report includes the following contents. Global electric vehicle industry promotes demand for lithium compounds. According to Tianqi Lithium Industry 2020 reports, China's electric vehicle sales of 1.2 million, accounting for 45% of the global total. Lithium carbonate consumes 80,000 tons. The U.S. expects global lithium carbonate demand to reach 900,000 tons in 2025. Controlling lithium resource is a key to new energy automotive industry. In China, over 80% of the lithium reserve in China is present in Salt Lake brine. And in Chinese Salt Lake brine, the magnesium-lithium ratio is very high. For example, Chang'an Salt Lake brine is the mass ratio. The magnesium-lithium mass ratio reaches 400. Looking for high separation performance, low energy consumption technology is essential. Difficulty in separating magnesium-lithium ions because the ionic radius of magnesium-lithium is similar, and the difference in hydration radius is small. But magnesium is divalent and lithium is monovalent ion. Hydration energy of magnesium is 4 times of that lithium. The challenge is how to design high polymer selectivity nanofiltration membrane. In recent years, nanofiltration membranes has drawn great attention from researchers. The separation performance of magnesium-lithium was improved by adding nanoparticles to adjust the process. Other active layer was positive charge was prepared by charging the composition of the separation layer. However, material design and construction are easy to defects and difficult to mass production. Nanofiltration membrane with positive charge prepared by IP. Separation factor up to 13.3. But the surface of positively charged membrane can be easily fouled by organics. Literature reports fairly good separation performance for monovalent and divalent cations by LBL nanofiltration membrane with great permeability. We first tried magnesium-lithium separation and surprisingly found that LBL nanofiltration membrane has excellent magnesium-lithium separation performance. LBL multilayer membranes are prepared by alternating deposition of cation and anion polyelectrolytes. LBL method can precisely adjust the process and charge. It is water solution, thus green and safe. Cost is low. so we use the PES hollow fiber ultrafiltration membrane as support. We use PSS as polyanion, PAH as polycation. Their alternately coating layer has 2.5 barriers, and it was cross-linked with GA. After LBL, the inner surface shows dense defect-free coating. We tested the molecular weight cutoff of this membrane. We found MWCO about 188 delta. We suspect that the unique properties of the LBL separation layer may contribute to this best performance. Pore size acts as the most important staving for separation mechanism and lithium. The hydrate radius of mechanism is 0.38 nanometer, smaller than that of magnesium 0.43 nanometers, and the hydration energy of magnesium is 4 times of lithium hydration energy. Lithium tends to lose hydrate water molecular with reduced size, so the rejection of magnesium was the highest, 99%. Lithium rejection of 66%. Interesting, the permeability of LBL nanofiltration hollow fiber membrane higher than 50 LMH per bar. We further tested the mixed salt of magnesium chloride and lithium chloride with total ion concentration of 2000 ppm as the mass ratio of magnesium-lithium between 20 to 60. We found high separation factor ranging from 71 to 75. The separation performance of LBL membrane was strongly influenced by salt concentration. Figure CD shows that the separation factor decreased from 71 to 47 when the feed salt concentration increased from 2000 to 6000 ppm. We further compared the permeability performance of our LBL nanofiltration membrane with report results in literature. The PSS pH 2.5 barrier LBL membrane shows the highest separation factors. The membrane surface was negatively charged at pH 7 according to the zeta potential measurement. Based on Donan effects, magnesium rejection should not be very high. However, the nanofiltration membrane rejection of magnesium about 99%, which is extremely high. This contradicts to Donan exclusion model. For 2.5 barrier PSS PAH ending with PSS, the outer layer is strong polyanion. The outer layer is negatively charged. This layer leads to dissociation of PAH in the sublayer, resulting to an internal structure with positive charge. We estimate that our PSS-PAH multilayer has negatively charged surface, but with positive internal structure. It looks like a sandwich. Donan exclusion by the positively charged sublayer contributes to high magnesium rejection. A 4-inch module was fabricated and tested in the laboratory. The module length 400 mm with 2000 hollow fibers. Surface area is 2 square meters. The rejection of magnesium was 99.9%. The separation factor of magnesium lithium is as high as 176. To conclude, for the first time, we showed air-bare nanofiltration hollow fiber membranes for magnesium lithium separation with a very high separation factor and high permeability. The rejection of magnesium was as high as 99%, with a separation factor of 74, setting a record of permer selectivity for magnesium lithium separation for engineerable membranes. Both size exclusion and donor exclusion contribute to the high separation factor. We proposed a novel sandwich structure. Top surface is negatively charged, and inner structure is positively charged. Future research will confirm the sandwiched structure using instrumental analysis. The research was supported by NSFC. Thanks to all members of membrane material and separation technologies, Shanghai Advanced Research Institute, Chinese Academy of Science. This is the end of my presentation.
Okay, thank you very much for the nice presentation, Rongrong. Thank you. But we have no time to ask more questions about this. I think we can contact Rongrong by emails after this conference, okay?
Okay.
Okay, thank you. Let's move into the next speaker from Huazhong University of Science and Technology, China. Welcome, Professor Qiang Zhao, to give us a talk about the ionic liquid nanofiltration membranes for lithium separation from salt lakes. Thank you. Please.
Well, thanks a lot. But at first, probably the last speaker should. Okay, now I can share my screen. Okay. Good afternoon, everyone. First, I would like to thank the organization committee to put us together to have this online session for sharing our ideas about membrane research. My name is Qiang Zhao from the Huazhong University of Science and Technology at Wuhan, and my talk today is elegant nanofiltration membranes for lithium extraction from salt lakes. I think the good thing to take part in this symposium is that we don't need to give too much background introduction, since everybody here seems like to work on nanofiltration membranes, which is really fascinating because of its versatile roles in many sectors of applications, such as water softening, diet separation, and here the topic is lithium extraction from brines. And lithium, as nicely introduced in the previous talk, has been playing very important roles in new energy, aerospace, glass, biomedical, and also rising areas. But the main problems for China is, like that said in the previous talk, is the high magnesium to lithium ratio. And when we are talking about nanofiltration membranes, most of the membrane currently, in addition to some new rising technologies such as layer by layer mentioned in last talk, the dominating one is still the interfacial polymerization, in which the acrylic chloride monomers dissolved in organic phase will react with amine or hydroxide containing monomers dissolved in aqueous phase to form a very thin layers, which probably like 1 to 200 nanometers. And the main mechanism for nanofiltration is a combination of pores, which is the size saving and the charge repouching effect. So if we look into the types, I mean the chemical structure of the aqueous monomers and organic monomers, in particular the aqueous monomers, you will have seen that these monomers are basically neutral or weak electrolytes, which means containing amine groups. They are not strong cation or strong anion groups. So our motivation in considering the structure of the monomers is that can we introduce liquid monomers into the polymerization reactions? If we look into these liquids, it features charge, strong charge, coming from the delocalized ions such as imidazolin, pyridine, and even phospholipid. But these monomers have been not so frequently exploited in interfacial polymerization. So we went to the monomer design. For a conventional monomer, we have a pros and cons analysis. They feature less hydrophilicity, but if you introduce strong charge into the monomer, you improve the hydrophilicity and you improve the charge density. But the side effect is that the charged monomer usually feature slower diffusion in the organic phase, which could be problematic in interfacial polymerization. And our motivation to compensate this side effect is to introduce more reactive amine groups. So here is the summarization. We proposed a series of new monomers. If we look at it at the blue columns, which are conventional monomers, you will see the permeability or permeance of these membranes made from these monomers are usually between like 4 to 10 liters per square meter per hour per bar. But when it shifted to when you introduce strong ions into the monomer, like the three red columns in the standing in the right, you will see the flux will improve drastically. I will not go into details of this work. If you are interested, you are referred to the paper cited right here. What we are interested, I will give you an example of how the structures changed after modification of these strong ion monomers. Basically, you will see the membrane becomes thicker and the roughness will larger and the contact angle are decreased, and more importantly, the mean pore sizes were increased. Let's take one of these monomers, for example, this monomer on the upper right corner, upper left corner, which abbreviated as THPC. It is a monomer from the phosphorus industry, and the precursor for producing this one is hydrosos in industry. So it is very important to reutilize this monomer. And the thing, when it was put in the aqueous phase, can react very quickly with the organic phase and forming very similar, as you can see from the photographs at the bottom corner of the pictures. And then by using FTIR and XPS, we can really verify that the membrane undergoes esterification reaction with the aqueous, with the organic phase monomer to form the same film. And then we tested, these membranes were tested by cross-flow nanofiltration. The most important feature, as you can see from I should call it blue bar or what, this column, which means that the flux was improved by more than 7 times. And still, it is noteworthy that the permeability is stable versus the operation time at a relatively moderate pressure of 2 bar. And if you compare this permeability with state-of-the-art membranes, you will see it is among one of the toppest, that is most permeable membranes among the literature, although the others are maybe two-dimensional membranes. And also because of the phospholipid introduced, this structure confers the membrane with antibacterial property combined with this high permeability. That we see the monomer introduces not only more permeability, but also the antifouling properties. Then comes the thing that we are concerned. Mostly the membranes that show higher flux may probably have much better hydrophilicity or roughness. But if you compare these parameters, you will see after the modification, the membrane thickness will increase, but the surface roughness in this case is almost the same. That is 23 compared to 20. And the contact angle, of course, was reduced, but not that much. So we sort of suspect that the surface properties of this membrane is not playing a major role in giving rise to such a high improvement of flux. So what is the reason? By using the cutoff experiments, we found that the membrane mean pore sizes will increase from about 4.5 angstrom to 6.2 angstrom. That is, the membrane become neutral. And by simulation, we show that the FFV, which is free volume fraction of free volume, was increased from 11% to 15%. Both results point to a speculation that the membrane becomes looser with larger pores and more pores because of the surface modification of these strong iron monomers. To further verify this speculation, we collaborate with Taiwan, with Huiran Li, Hongwei Song's group in Taiwan, and use this positron experiment, this fancy positron experiment, to really characterize the fine structure of the membrane, which I mean the free volume. The good thing that we can use the slow beam model by defining the electron energy. We can detect the free volume profiles of this membrane at different depths from the top down to the membrane. We see that from the right, the figure in the left, you can see at the depths of about 16 nanometers down the membrane, we see the modified membrane, which here represented by the color curves, shows more or larger free volume cavities. That means we create larger pores at the very top surface. And when you go down to the deep of the membrane, you will see the free volume percentage was increased. That is, if you put these two figures together, you could image like this. At the very top surface, the membrane becomes looser, the pore become larger. And when you go down to the membrane, middle part of the membrane, the dense part of the membrane, you will have more pores, although the pore sizes are maintained. Through the combination of this mechanism, the membrane permeability was highly improved. To further confirm this speculation, we synthesized 3 more control molecules to verify our speculation. As I show right here, the control monomer without strong iron shows very permeance, which is probably due to the dense structure. And when you introduce charge here, like the catalyzed nitrogen or the phospholene or the catalyzed nitrogen here, both of these two membranes are highly improved in terms of the water flux. And the flux improvement is positively correlated to the amount of the ion liquid you introduce to the membrane. So by using these control molecules, I think we got sort of backup of our mechanism we proposed. With this in hand, we go further to design more ionic monomers, especially for the lithium and magnesium separation. Here is one example we show. Like we designed a DAIB monomer to modify the PEI membrane, and we found that the flux was improved by almost 4 times, while the selectivity was maintained. What's more important, as we know, those membranes, although gives high flux, are susceptible to high pressure or operation time. But here, the flux is sort of stable operation versus operation time, which means it indicates its practical potential for high pressure applications. And then we set up a sort of 2 cycles operation for the magnesium and the lithium separation. By doing so, we are able to reduce the ratio, magnesium to lithium ratio, from 50 to about 1 or 2, and combined with very high permeability by using this membrane. So I think it indicates some sort of efficient and economic advantages of this membrane. And we also goes into details of the separation mechanism of this new membrane for magnesium separation. We did simulation and the characterizations to test both the surface and internal, the bulk part of the membrane. And we found that the membrane surface has a hydrophilic property, while if you go deep inside, it has sort of less hydrophilicity. That is, both the absorption and the diffusion was accelerated because of the surface modification, which leads to high membrane permeance. With this in mind, we also have a couple of works which is still in preparation. I hope can be published in near future. We also expanded the scope of this monomer. In previous talk, we use this monomer for surface modification, and the ultimate goal for us is to use the monomer as a real monomer for the straightforward interfacial polymerization. We are right on the way, but we are now able to figure out some of the useful structures for this purpose. And the membrane, as you can see right here, is combined shows a good combination of flux and selectivity. And the important thing is that it is not conducted by surface modification. It is used for straightforward interfacial polymerization. And the last slide of my talk is about polymers. We have allyliquid. We also use polyallyliquid. The polyallyliquid, when it was used as aqueous monomer, features very good advantages to prepare thinner membranes, such as 30 to 50 nanometers. These membranes use also very high permeability combined with good selectivity. With all this, I think I would like to come up with a very brief conclusion. And the first thing is that we try to show that the active rules of allyliquids in interfacial polymerization and the preparation of thin film nanocomposite membranes. We designed a series of allyliquids, both for surface modification and for straightforward IP. And second, we want to show the strong ion effect can improve pore ratios and the lithium extraction efficiency. And we believe there are still much more things to be discovered in terms of what is the exact rules played because of the strong ion effect in the membrane structure. With that, I would like to come to an end and thank all the students, postdocs who work in this project and the fundings to support us, and of course for you for your attention. Thank you very much.
Okay, thank you very much for your excellent presentation, Professor Zhao. Okay, you have done lots of work for the membrane with ionic liquid as monomer, right? So, so which ionic liquid is more suitable for the membrane preparation?
Excuse me, sorry, it was not clear just a moment. Could you please repeat it again?
Oh, okay. I mean, you have worked very hard for studied the free volume of the membrane with the ionic liquids, right?
Yes,
So
yes.
I just wonder which ionic liquid is most suitable for the membrane preparation with the interfacial polymerization techniques.
Okay, okay. So far, we figured out two principles to design the suitable ionic monomers. First, it should contain multiple reactive groups, such as amine or hydroxyl groups. So far as we know, if you have like just one single amine groups, the reactivity is too low for forming these defect-free membranes. You need to have more amine groups in one single monomer. This is the first thing. The second thing is that it is better to have a liquid with bulk size, I mean bigger size, to really enlarge the free volume of the interfacially polymerized membrane so that you have a proper combination of flux and selectivity. This is what we have right now.
Okay, another short question is about, can you explain the reason of the separation factor of magnesium and lithium is so high?
Actually, in our work, the selectivity, I would say, is modest compared with state-of-the-art work. The advantage, the most sharping advantage of this membrane is not selectivity. It is the flux. The selectivity of our membrane is about 10, which is average compared with other polymeric or polyamide membranes. And when you want to know the separation mechanism, I think the charge repulsion, the combination with charge repulsion of size 7 is the dominating one, which usual as that is widely accepted by nanofiltration membranes.
Okay, thank you, Professor Zhao. Due to the tight time, let's move into another speaker. Okay, Professor Elma Tafa from the United Arab Emirates.
Hey, greetings everyone. Let me share my screen, and I'm still not a professor yet, but thank you.
Okay.
All right.
Well,
yeah, I'll start right in a bit. Well, welcome everyone, and thank you for this wonderful presentations. The topic that I'm going to present today is a little bit could be different than the membrane filtration kind of family, but it feeds in at the end of it. My name is Gayaf Mustafa, and I'll be presenting a topic about the design and application of hydrophobic TMPD-based deep eutectic solvents for boron extraction from saline brine. Now, I know this is a long title, but trust me, by the end of this presentation, you're going to enjoy it much more. And I always start by the end in mind, which is boron extraction. Boron, in general, it has several uses. It's used as detergents in ceramic. It's used in radioactive wastewater plants, in nuclear wastewater plants. It is an essential micronutrient for both animals and plants. However, if used excessively, it could affect the fertility of certain animals, and it could be detrimental for particular crop yields. Now, for us humans, although we give it a label, but there isn't any statistically significant effects on our health. In fact, it's useful for our bones. So why do we remove it? We do that either as protective measures, such as protecting our agricultural crops and meeting drinking water requirements in desalination plants, or as productive measures, where we want to recover boron from wastewater industries, or as the previous speaker just said, to recover it from brine. Well, how do we do that particularly? In this particular study, we used the most mature and the mature solvent extraction process, or also known as liquid extraction. Basically, you have a liquid phase where we have boric acid as the contaminant in that liquid phase. And we want to have an immiscible organic phase in which we have an alcohol in that organic phase. We mix and shake for a period of time, and the boron and the boric acid will move from the aqueous phase to the organic phase through an esterification process. Now, this brings me to my next term in that title, which is the TMPD, or 2,2,4-trimethylenol-3-pentanediol. Now, this diol particularly has two hydroxyl groups in such an arrangement that it allows it to form very stable complexes with boric acid. This TMPD molecule has been studied since the 1970s, and it was predicted back then that it's going to replace other boron extractants. Later in 1995, further studies used TMPD in different organic solvents and studied it for boron extraction, where it showed stability constants, very efficient extraction efficiencies. And the studies piled up since then. But nevertheless, all of these studies used or depended on highly toxic solvents such as sulfonated kerosene, chloroform, or carbon tetrachloride. This brings me to my next term, which is deep eutectic solvents. Now, what are those exactly? Basically, you have a component A with a melting point A and a component B with a melting point B. Now, we mix and share. Sorry, can you see my screen? Hello?
Yes, we can see.
Okay, I'm sorry. I thought I lost connection for a second. Yeah. So we mix and shake those two components, and the resulting mixture has a depressed liquid, depressed melting point compared to the individual components. Now, this is a very simplified version of the deep eutectic solvents. This is the eutectic mixtures. I want to just step aside and explain the deep eutectic part, which is basically done through the deviation from the ideal behavior of a two-component mixed together, because any two components mixed together will behave differently. And that deviation from the ideal behavior, from the ideal temperature behavior, is what we call a deep eutectic solvent. And this is what we measure experimentally, the deep eutectic part. So in general, to sum up what is deep eutectic solvents are, they are a mixture of components. The components maintain their identity and have interactions through hydrogen bonding, and those results in a melting point depression of the final component, thus having unique properties that are not there in the individual components. This is in simplified deep eutectic solvents. And this is basically what we are trying to do here. It's to design and apply these kind of deep eutectic solvents for a target applications. I'm going to show you the framework that we discussed here for the development of these. So it's basically on 4 phases: the development, validation, characterization, and optimization. For the development phase, we basically focused on the selection of the right materials to form the hydrogen bonding for the DESs, and we depended on the thymol and menthol as the hydrogen acceptors and TMPD as the hydrogen donors. And that was not an arbitrary choice. Thymol and menthol are intrinsically hydrophobic. They are natural and renewable materials. very cost-effective, cheap materials, and they have been tested before to form very hydrophobic, stable hydrophobic epitectic solvents. Likewise, for TMPD, it's a stable at room temperature, solid active at room temperature. It's a mild irritant, very less toxicity, and it's a comparatively cheap compound, and it has been used before, as I showed. Now, what does the validation step looks like? We mix them. It's in 4 steps as well. It's in the formation. We first test the formation and the stability of those components in room temperature, the epitectic solvents. And then we test the hydrophobicity of these because we need to test them for water application. Then we do some preliminary studies to apply to prove that they are extracting boron, and then we end up with a valid DES for this specific function. Now, as for the formation step, we mix the TMPD with thermal or methyl in different ratios, starting from 8:1 up to 1:8. And you can see that they have been stable for a quite period of time. This is in the liquid state. FYI, both components are originally solid. And then when you mix them together, they depress, and the depression, the melting point brings them into that state. Now, for the hydrophobicity, we mix those components in a 1:1 ratio with DI, plain DI, to see how stable they are. And you can see like right away that components with TMPD ratio 8 and TMPD ratio 4 for both thymol and menthol have solidified, and they were not stable. So we exclude them immediately from the liquid-liquid extraction studies. As for the characterization, it is very essential to study the phase behavior and the thermal stabilities of these solvents, and we do that using DSC. As you can see right away that compared with the 2 components, the methyl and the system and the thymol system, they both, from the ratio of 2:1 up to 1:2, have a very depressed melting point. And in fact, we could not detect a melting point. This is the glass transition point. And I have plotted in the dashed line here the ideal behavior. This is how it should ideally behave. And this feeds into that definition that I showed you earlier, that the deep eutectic solvent is how much depressed we are based from the ideal behavior. And this is granted for both systems. Now, furthermore, for the characterization step, we wanted to know what kind of factors are influencing the solvent extraction process. And these are factors such as density, viscosity, water solubility, and the leachability through TOC. And these are all related to the extraction efficiency per se. So we plotted and visualized those properties for each of the components in the same graph. And you can see that there is a significant effect of those properties on the extraction efficiency as well. Both density and viscosity, for example, they increase, or at least viscosity and leachability, they increase with the higher ratios of TMPD, which we want to avoid. Viscosity specifically governs the mass transfer rate, and the leachability governs how much loss of DES that we have. Same thing can be said for the menthol TMPD system. With the higher TMPD ratios, we're getting an amplification of these critical aspects, the leachability and viscosity. So it is wise decision to choose a balance from that ratio, although it is doing the functional extraction. So we choose 2:1 menthol to TMPD for both systems, the menthol and the thymol. You can see that this is the first step of optimization right there. But again, to further use, or technically, since we've done with the design part, to show you the application part, we tested those DESs for different parameters in the boron extraction process, such as pH, temperature, initial concentration, and the aqueous to organic mass ratio. And you can see that we've compared to the literature what we have before, it was a superior performance, mainly due to the TMPD role in this eutectic state that has been granted with the DES. But it doesn't stop there. We've also tested it over multiple extraction cycles, and we confirmed that it's stable with very minor losses over 3 cycles. And this also feeds into what kind of application that we're looking at, and that was the saline brine. And as the previous speaker said, in any lithium extraction process as well, or most of the lithium extraction process, there is boron presented in the feed itself, in the matrix of the solution itself. So boron extraction usually done as a pretreatment before the lithium extraction process from saline brines. And you can see right away the saline brine is not an easy matrix. It contains multiple components, lithium, sodium, magnesium, potassium, calcium, and so on and so forth. So we prepared a surrogate of that solution and we tested it for boron extraction under these extreme conditions. And apparently we have very selective extraction process with the 99, it was even higher extraction efficiency at 99% with no extraction with the other components. And that was kind of expected because you are expecting TMPD to complex with boron through the complexation of the 6-member rings that I showed earlier, and not with the other ions. The increased efficiency, I wanted to add a comment based on what I've seen from the presentations before, is actually due to the salting out effect, where the other molecules are contributing and being hydrated, the other ions, thus virtually creating more boron in the water. Well, that was the design and application part, using what we used, like those deep-protective solvents. They are much more cost-effective, green solvents, and they grant us those kind of superior properties. But it doesn't stop there. The optimization part doesn't stop at developing the DS. What if there is more? What if we can change this cyclic group into an aliphatic group? Well, it appears that actually also there is always more tweaks that you can add to your system so that you can improve on what you've done. And this is basically what happened when we changed from the aromatic to the aliphatic. We had a much lower viscosity and density, and this is favorable for the solvent extraction process, where you want a better phase separation from the water and you want a higher mass transfer rate. And you can also combine them with different components in a ternary deep-protective solvent so that you can even tweak it more and more. So the possibilities are like, there's virtually a whole number of possibilities, such as in the ionic liquid field. The DES field is also in the same family where you have multiple recipes that you can measure. The end goal was also to start using that or transforming this solvent extraction process into a supported liquid membrane diffusion process, as the first speaker presented. But it appears that to stabilize the DES into the membranes, this is another story that requires another radar plot to study the different performance and the different metrics that governs that process. But this is going to be in our future work, hopefully. In the end, the framework that we designed here grants you the full process where you can design and apply your deep-protective solvent for a target application, starting by the selection of the material, moving forward by the validation studies and the characterization experiments so that you can know the physical-chemical properties governing that system. And in our particular case, we are utilizing the long-lasting love relationship between TMPD and boric acid, of course, supported by different materials as needed. I want to acknowledge the efforts of Professor Inas Al-Nashif and Professor Hassan Arafat. I've been with that project since 2018, and we've marched a long distance since then. I also want to acknowledge the collaborative work of Professor Ayanis and Professor Hadid from Abu Dhabi University. And lastly, I cannot forget the nerds in the kitchen, Engineer Nergis, and finally me. Thank you very much for attending that presentation. And if you have any questions, please let me know.
Okay, thank you very much for your interesting presentation. Thank you very much. Because of the tight schedule, we have to move to another, the last presentation talk from Qiuming Ma. Professor Qiuming Ma?
Yeah, I'm here.
From the Shanghai Jiao Tong University of China. Yes.
Yeah, just a moment. Let me share my screen.
This talk is about membrane distillation system.
Saying that I cannot share my screen because somebody else is sharing.
We have not seen.
Okay, I guess now it's okay.
Okay, we can see.
Yeah, thank you.
Please.
And yeah, so I start. Greetings from Shanghai, China. And yeah, to all the professors, especially thank you, Professor Xu. And greetings to all the professors and fellow researchers. And I'm sorry, I've been a little bit under the weather these days, so I have a sore throat and might be coughing from time to time, but it's definitely not COVID. So yeah, and I'm really glad to have this opportunity to present at the Mendes 2021 conference. And my name's Dr. Qiuming Ma from Shanghai Jiao Tong University. And currently I'm working as a postdoc in the ITWA team as the top left corner, innovative team for energy, water, and air. And our ongoing work is titled Parametric Study on the Dynamic Performance of a Passive Solar Multi-Stage Air Gap Membrane Distillation System. And this work is supported by the Shanghai Science and Technology Committee, as well as the China Postdoctoral Science Foundation. And my presentation is going to be in 5 parts. First, a brief introduction. And the target of our ongoing work is for a small desalination device for the remote coastal areas and isolated islands. In such application, it requires probably a small scale device and easy to operate. And for currently mainstream desalination technologies are usually categorized into 2. First is thermal distillation and membrane separation, and the majority of the technologies actually all have some obstacles in applying to our target application. So we have to come up with some better solutions. And so here we tried membrane distillation as an emerging desalination technology, because it has several advantages from both of the desalination technology categories, and especially for the merits of low working temperature. And when we consider the application scenario in remote coastal areas, in some remote areas where energy supply could be a problem, solar energy can make up to this point to link the merit of low working temperature to the energy supply for our membrane distillation process. And we consider it might be a good choice. So some basics about membrane distillation. I think it's well known, so I'm just gonna simply skip that, I guess. You have the most studied types of membrane distillation, surely AGMD, air gap membrane distillation, vacuum membrane distillation, direct contact membrane distillation. And specifically for air gap membrane distillation, because of the air gap between the membrane and the condenser plate, it suppresses the conductive heat loss from the feed side to the permeate to the condensation. So it ensures a higher thermal efficiency. And also due to the same structure, it enables the possibility of internal vapor condensation on the condenser plate to recover the heat, and which is essential for the scenarios where the energy income will be a limitation. Sorry. And then the module configuration. We designed a photothermal multi-stage AGMD device as shown in the picture. And it's passive. It can be in passive operation and can be floating on the water surface. As you can see, there are 3 stages in our current design. The top stage, the membrane is the photothermal membrane. I'll introduce it later. And the bottom 2 stages are just normal membrane. And all 3 feed layers are connected in series. And we use some weight to float the whole device just a little bit above the water surface. And for the membranes, we just use commercial membranes with the PTFE film and the PET supporting layer for the 2nd and 3rd stage. And for the first stage, because we in our design we used the photothermal membrane, so in our lab we made it ourselves. We purchased 100 milligram of carboxylated multi-wall carbon nanotubes and disperse it into 30 milliliter of isopropyl alcohol for 6 hours. Then we maintain the commercial membrane onto a heated platform at 130 Celsius degree and spray the solution onto it. And after drying, we hydrophobize the made photothermal membrane to obtain the final product. And after inserting the photothermal membrane and everything else, the device looks like this. And if we float it on the water surface, it looks like in this picture. And the whole test record, we use the simulated solar energy. We use the Science Tech solar simulator. And for data acquisition, we use Agilent. And after the experimental setup, now I'm moving on to the modeling and validation section. For modeling, we use COMSOL version 5.6 with some major simplifications as shown here. And for the solar income, we assume a one sun condition, 1000 watt per square meter. But when we consider the transmission by the cover and first feed layer, and also we measured ourselves, so we used about 930 watt per square meter for the solar income. And the parameter settings are according to the real experimental conditions, as well as the real material properties. And COMSOL, of course, COMSOL don't have a specific module for membrane distillation, so we have to insert some calculations and some user designed elements. And for the performance indicators in our simulation, we simply use production rate, which is common, and also distillation efficiency. It's defined by the latent evaporation heat that from of all the production water against the solar energy income. And for the fluid dynamics for the device, it's we just let it governed by COMSOL. Then we have to insert the calculation about transmembrane heat mass transfer, most importantly, the Premier flux, using the typical equation with the calculation of the coefficients. And for the losses, we consider the convection and radiation heat losses. And last, as mentioned above, we consider the solar absorption as a uniform heating source at 930 watt per square meter at the membrane, at the photomembrane surface, actually. Then after the model, we have to validate the model with the experiment. Yeah, for the experimental device, the size is 100 millimeter in square, both in square, yeah, both in length and in width. And also for the simulation, we have the same setting and the thicknesses of each layer, the same settings. And we ran the experiment as well as the simulation for 1 hour. And after all the study, we can have the graph as the dynamic feed temperatures of all 3 stages. And after the simulation as well as the experiment, we can see the production rate between these two are pretty similar, pretty close. And for the temperature, dynamic temperature, all the average deviation of each stage of the temperature average deviations are all below 5%. And when we look at the temperatures from point to point, the biggest deviation is still below 10%. So that's the model validation. After validating the model, we played with some parameters to see how the device responds to the variation of parameters. First, we varied the feed layer thickness, also the same 3-stage module and the same size. And we consider 5 different thicknesses of the feed layer. And we can see that with thinner feed gap thickness, both the water productivity and energy efficiency has an enhancement. And when we extract the two extreme conditions with the thinnest thickness and thickest thickness, you can see all the temperatures in all three stages are all higher in the thinner feed layer setting. And also it responded faster than the thicker feed layer, because when the feed layer is thinner, the heat transfer is better, and also the energy is less used to heat up all the bulk feed. And after the feed layer thickness, then we varied a little bit of the air gap thickness. The similar trend we found is with thinner air gap thickness, also the performance were better. But differently, actually for thinner air gap thickness, each layer, the temperature is somehow lower than the thicker air gap thickness setting. And because what we consider it is, I think is about the heat and mass transfer resistance in the air gap. Because when the air gap is thinner, both the heat and mass transfer resistance reduced, and the reduction of heat transfer resistance will increase the conductive heat loss through all the layers. So it's detrimental to the overall performance. But the thinner air gap also ensures a better mass transfer condition. So here we can see from the final performance, we can see that actually the thickness of air gap actually has a more significant impact on the mass transfer. And additionally, we can see that because all the temperatures in each stage are lower with thinner air gap thickness, in that case, the heat loss to the ambient seawater or the air can be lower because the temperature is lower. That also contributed to the higher performance. And then we tried different state numbers, and we tried longer operational time in simulation. And for different stage numbers, we tried up to 7 stages. And clearly the performance were better with the larger stage numbers. But we found that actually after stage number 5, the enhancement were limited. And at the stage number 5, actually the energy efficiency could reach 140% with impressive productivity. And for longer, we also tried longer operational time because all of the above operation were just 1 hour. And with the prolongation of the operation time, you can see the performance first augmented a little bit, then tend to stabilize. That's because the whole device, the MD process, they have an initial stage, because at the beginning the temperature of all the feed layers are just the same to the outside surrounding seawater. And with the solar income, the temperature going to reach to a certain point where the MD process can happen. So with longer operational time, actually the initial stage, the impact of the initial stage can be lessened. And that's why we can see this trend similar to the stage number. So lastly, the conclusions. Here in our lab, we designed a photothermal multi-stage AGMD module, which is totally 100% solar energy powered without extra energy demand, and it can be floated on the water surface for a passive operation. And we built the model in COMSOL, and it's validated by our experiments. And when we play with the parameters, we can see with the thinner feed layer and air gap, both the water productivity and energy efficiency could be increased. And when it comes to higher stage number and operation duration, also the water production rate and energy efficiency increased, but they first increased, then plateaued. To give you an exemplary performance for a 5-stage device with the air gap thickness of 4 millimeter and the feed layer of 2 millimeter, and for maybe operates for 3 hours, we can have a water productivity at 2.16 kilogram per square meter per hour, and at an energy efficiency at 144%. Our ongoing work includes first the fabrication of the 5-stage module to conduct the experimental study. And also we're trying to modify the module. For example, recovering the last stage, instead of dissipate the heat, the heat of the last stage to the ambient seawater, we recover the heat to right back to the first stage. And also includes flow path alteration. For example, the feed layers can be in parallel or in counter current. And lastly, we are running some long-term operation to examine the resistance to salt deposition and the measures to resist it. And thank you all. That's all. That's all my presentation.
Okay, thank you very much for your nice presentation. But I'm sorry, there is no time to ask questions.
Yeah,
so
if
somebody here, if anyone have questions, please contact Professor Ma by emails, okay, after this conference. Okay.
Yeah. I'll type in my mailbox into the chatting box.
Okay.
Thank you.
Okay.
Okay, this section is going to be end. I think we gain a lot from this outstanding and interesting talk. So let's thank for all the speakers and audience. Have a good day, everyone. Bye-bye.
Thank you. We will, if you have time, please go to poster session. Thank you.
Yes, please move to the poster section. Okay.
Okay. Thank you, Professor.
Thank you, Professor Ma.
Bye.
Thank you.
Thank you, Professor Tong.
Bye.
Yeah.